addressing format? Not exactly, but it's kind of a not a the segmented addressing. And here's the key phrase. You're talking about real mode here. In real mode, each logical address points directly into physical memory location. Okay, that's the simplest thing, and even then, it doesn't point directly into a physical memory location. Kernel never gives access to ring 0. Probably not. Probably not. All right, so we've got real mode. Each logical address points directly into physical memory location. And even that's not entirely true, because you remember that the reason, let me back up as to the reason why we have this segmented addressing in the first place. The internal bus on the 8086 has how many bits? Does anybody remember? Reason it's an 86. Internal bus on an 8086. 16 data bits, Matt, exactly right. He will give you the gold star. But it has 20-bit addresses, right? So how does a 16-bit bus come up with a 20-bit address? Question mark, question mark, question mark. See how good you guys remember from the first week or two of class. Hint, hint, hint. Multiplexing. Actually, the answer is on the slide in black bold in the top left corner. Right here. Segment addressing. There you go. Segment addressing. Now, you don't know what you said, but you did say it, and you answered the question correctly. Both of you. Congrats. You did right. So the segment addressing, in fact, is how they do it. What they'll do is you take the two 16-bit addresses. You're going to use two segments or two lines to get an address, and then you offset them by 4 bits. And you remember we would kind of add them together, and there was a segment basically is as big as, it has 16 different locations in it. That 16 locations is 2 to the 4, the 4-bit address difference. And that's kind of how, that was sort of the kind of the ideas they were coming out with the 8086 was, boy, we want to have 20-bit addressing. Let me ask one other quick question. Can anybody guess why we would want 20-bit addressing? We'll really push you guys on this one. I'll give you a hint. 4 megabytes of data. Actually, it's 1 megabytes of data. And 1 meg, exactly. 2 to the 20th is 1 meg. If it was 4 megabytes, we would have 22 address bits. So 1 meg. Good correction, Matt. And when we're talking about that, it was kind of a magic number. It was a marketing number. If you could get 1 meg of RAM, you were doing pretty good back in those days, which is something you guys wouldn't know or remember. But again, the idea of the 1 meg was that 2 to the 20th gave you that magic number of 1 meg, and the marketers could say, we got 1 megabyte of RAM, and that was cool back in the day. So it's always interesting to me how science interacts with marketing, and marketing interacts with science, and politics stirs in the whole mess. One big CPU cache is yawning. Thank you. Cute joke. I'll take it. All right. So bottom line is we got the 20 bits. They wanted to get to 20 bits of addressing, but they only had a 16-bit internal bus. And so what they did was they created the segmented addressing where they shifted it over by 4 bits, and you had segments and offsets, and they started coming up with this whole kinds of different ideas. They took that further into the virtual addressing quagmire we started wading through a discussion or two back. Okay. And then they took it to the next level where they decided to have this protected mode addressing, and they built that into the address itself. Okay, so it's really tough to get in and out of something that's not built into, when it's built into the address, baked into the address itself. Okay, so what we're talking about here then with the segmented addressing, remember we used to have physical address is equal to the segment part times 16 plus the offset. Okay, and that's if the address line 820 is enabled. Now remember that 820 would be 21 address bits, and they're kind of pointing that out here a little bit. Every segment has a size of 2 to the 16th bytes. All right. So bottom line is the segment addressing is the real mode you cook up an address that actually can get to by all 20 address bits. Now, what you do is if your actual memory wasn't a whole meg in size, and that did happen back in the day, and again, what was it you were saying? Your 1 meg CPU cache is yawning. Yeah, it's probably more than a 1 meg CPU cache these days. But that the whole idea then was when they started to get bigger memory, actually, when the memory wasn't as big as the address space, that's where the virtual memory stuff starts to come into play. All right. So we did this one before too, by the way. We'll talk about protected mode in just a second. How big are most of the data buses in most of your processors these days? 64-bit. Very good, Matt. All right. If you have 64 bits, how big is your address space? Two to the 64. Okay, Colby, good. I'll take that. All right, so 2 to the 30th is a gig. 2 to the 40th is a terabyte, right? 2 to the 50th is a petabyte. And Matt, I think you've had a corner on 2 to the 60th, haven't you? What's 2 to the 60th official term? You looking it up for me? No, that was 2 to the 50th. Peta is 2 to the 50th. E something? Yeah, yada. Okay, I think yada sounds about right. I'll vote with that. It's not Latin because Latin is almost would be sexabyte, and most folks would take that in the wrong direction. All right, so yada, I think probably we'll go with that. So it's if you had a terabyte, okay, Ezekiel's going with yada byte too. I think that's probably close enough for the moment. So if you have a terabyte of RAM in your machine, you're doing pretty good, most of you, right? Yada byte equals 2 to the 24th. Oh, okay. Whatever it is. Okay, thank you for the number. Nicholas put up the whole number. This is what Google says. Okay. That's 2 to the 64th. Yibby byte, 2 to the 80th. Hello, I wish I had 1 terabyte of RAM. Me too. But if you had 1 terabyte of RAM, you're still only chewing up, what, 40 address bits? Right? Everybody with me on that? And you can't, if you had 1 terabyte of RAM, you're only chewing up 40 address bits, but your bus inside your computer, you can download or RAM. The bus inside more RAM. Okay, yeah, you can download or add more RAM, but you getting up to a terabyte, you'll be doing good. That's 2 to the 40th. Your address bus inside your machine is 2 to the 64th. So you've got a 1,000 times 1,000. You got 1,000,000 times more a multiple of 1,000,000 times more address space than you're going to get in a RAM in your best dreams. Okay. So what do you do with all that address space? Well, this is where your virtual memory stuff starts to come into play. And because you've got buku address bits that you don't really need anymore, or can't even really use all that much, you can reserve a few of those bits for doing special things. And that's where we're headed with the protected mode addressing. That's also kind of something that was originally dreamed up with the segmented addressing. Does that make a little bit more sense? Hopefully, to bring it down to the worst one. 14 gigabyte of RAM in your computer. Yeah, that's not bad actually. I'm trying to think it's been a while since I bought RAM, so you get, I don't know what they're coming in terms of standard size RAM stick these days, but 8 gig. Okay, 16 gig. Yeah, 16 gig, but 6 sounds right. 32, but it's slow. Okay, I'll vote with that. A lot of 32s. It may be, and a 32 might be 2 16 gigabyte sticks too, is a possibility. Tomorrow's got 8. Okay, all right. So in protected mode, the segment part is replaced. Okay, so here's what happens. We had the segment offset sort of thing. Remember those 4 bits that get offset? And with the protected mode, what we do is instead of having the 16-bit selector, instead of having the 16-bit segment, we now have a 16-bit selector. And now we start peeling off some of these bits and we use them for special applications. The 13 upper bits contain the index to an entry inside a descriptor table. Okay. The next bit specifies whether the operation is used with the GDT, the global descriptor table, or the LDT, and I think that's local descriptor table. I was looking for that. I didn't find it fast enough. I got question marks around that. The lowest two bits, 1 and 0 of the selector, are combined to define the privilege of the request. Okay, so I've got 4 levels of request. If I have 2 bits, I can then define 4 different levels of the privilege of the request. This means that the byte offset of descriptors in the descriptor table is the same as the 16-bit selector. You add them all up, you get 16 bits, provided the lower 3 bits are zeroed. I got 19 versus 16. Bottom line is they started expanding into more and more address bits, and they started coming up with some of this sort of stuff. The descriptor table entry defines the linear address of the segment, a limit value for the segment size, and some attribute bits and flags. How many segments are there altogether? Okay, in the original 8088 or the original 8086, there were I think your segment size is the offset. No, I'm going to take that back. Your segment is the segment offset was 16 bits, which is what you could have on your normal bus, and you use the extra 4 bits then to get up to 1 meg to decide to define different segments and so forth. All right, except that they would do it at the back end, at which point the segments would only be 16 bits, 16 locations different. So anyway, all right, kind of hand waving here a little bit. How many segments are there? Memory and bytes, 2 segments. There are, I'm trying to remember what the original, I think there's 16 segments. Am I saying that wrong? 16 segments, and each segment then would have held 64K worth of address locations. Should that add to 1 meg? Slide said 16 segments. Okay, good. I remembered it right. 16 segments on an 8086. Thank you, Matt, for looking that up. All right, so the segments are interpreted differently in the protected mode versus the real mode. All right, so now we're getting into the slides from Dr. Patel. The segment register contains a selector that selects a descriptor from the descriptor table. Okay, now so we're going to start nudging back then into this sort of kind of virtual addressing concept where something picks out something else, and then that something else then takes you off to where you really want to go. This indirect addressing sorts of stuff comes into play. Also, as I was putting this together, notice that we're talking about an EBX here. Remember, the X is for the extended stuff, right? So we're talking about, we still have some of the normal sorts of kinds of things that we'd have with the 8088 and the 8086, but now we're starting to talk about this protected mode addressing kind of comes into play in the 286. So we're starting to get to more larger address buses and doing more of this sort of kind of things. So bottom line is you would take whatever your base is, you would add that to your offset to give you your address location. And then from there, then you'd go into the data segment that you're working for in the protected mode addressing. In this case now, notice how many bits we have here, guys. How many hexadecimal characters do I have in the brown here? The red works too. 8. Colby, that's exactly the right answer. Nicholas has got 8 too. So if I've got 8 hexadecimal characters, then how many data bits is that? And I think Colby's already anticipated me. And there's 32 address bits. Okay. So this is what you look for. So this is a 32-bit field here. And the offset can be 32 bits. The offset then, when you add these two guys together, is going to take you into your data segment. Notice the memory system. How many characters do we have up here? We got all Fs. We're back to 8 characters. There's 32-bit addressing. So now when you're talking, this is back in the days before they would run around with a 1 gigabit stick of RAM. Okay. So the memory system, again, the same thing, but 30 years ago. The memory space would have given you 2 to the 32, which is 4 gigabytes worth of memory space, which I remember back in the day thinking, how in the world is anybody ever going to use 32 gigabytes of RAM. I mean, they don't even, how could you possibly fill that up? You guys have done that, I think, a few times, but the address space back then would have been much more than what we had. Google Chrome takes that much while it's sleeping. Okay. Photoshop, believe it. I'm sure you guys can think of different things that take up a couple of gigabytes worth of RAM these days. Microsoft Office, I'll give you that. Blender, Nicholas. Okay. Vista. Blender. Blender's a was that Blender's an operating system or something? Somebody help me out here. What's Blender? Minesweeper? Oh, come on, not Minesweeper. Autodesk Inventor. 3D modeling is Blender. Okay. Okay. All right. Wow. Cool. All right. So bottom line is, back in the day, though, this was, again, the virtual addressing concept that was going on. And this was the number of address bits you would have had to play with. So, all right, let's roll on ahead. We're kind of putting some things. So we're going to put in some specialized bits. Okay. There's this limit field. There's a base field. Okay. Limit is the length of the segment minus 1. All right. Actually, it looks like 16 bits to me, but and then you've got the base segment, the starting location of the memory segment. Okay. And then you've got this limit. 20 bits allows segments up to 1 megabyte. That's true. Length of the segment minus 1. Okay, so yeah, the limit would make sense. Memory leaks will take up a lot of RAM too. That's true. This value is shifted by 12 bits to the left when the granularity bit is set to 1. Okay. Granularity bit is going to define what the size is of your segments, I'm going to guess, but I don't know for sure. Here's G, the granularity bit. Okay, so you got some specific bits. Notice how many bits we have in when we went to the protected mode. Notice how many address bits we believe we started to have here. How many address bits do I have with this? Answer's easy. 64. That's correct. That's correct. So they were already playing around with 64-bit addressing, again, with specialized bits. In their mind, 32 probably would have been the top limit. Okay. I'm not sure this is going up to 39 and 40 here. I'd have to add some more stuff, but because that wouldn't be an even byte. 1, 2, 3, 4. Okay, that's why you have 40. You have 5 bytes. My brain's not clicking in today. So the base address then takes you up to 5 bytes worth of addressing bits, which would be 20. That would be the original top level there. Why did we have 39? Yeah, doing the math wrong. Okay, 20 is down in here. Okay, so this is going to be 32 right here, and that's going to be your 1 gig worth of, or 4 gig worth of address space. So they got yet one more byte they're going to put on when we're dealing with the base, and that gives you this big addressing space area. And then you're going to put special things in here to help you zero things in and create your protected mode addressing space. Okay. We're going to look at these different fields here in the next slide. So the G bit segments can be 1 byte to 1 megabyte in length. Okay. When G is set to 1, your upper end is going to increase, but your lower end is going to increase as well. So when the bit is set, then you have less granularity, but more memory space. When the bit is set to 0, you've got more granularity, but less address space. Okay. There's a user-defined bit. I honestly don't know what that's for, guys, but that's there. The D bit indicates how the instructions access, register, and memory data in protected mode. When D equals 0, the instructions are 16-bit instructions with 16-bit offsets and 16-bit registers. Okay. When you are in D1, 32 bits of addresses are assumed. This is the stuff assembly is doing in the background. Very good point, Matt. Very good point. Yes, it is. This is all well under the hood. This is not something that your normal program is going to think around with. This is all. Actually, not even assembly necessarily. I don't think assembly is even going to see this. This is going to be some sorts of stuff that I'll talk about this in a minute too, where it's all happening in the background. It's in the hardware itself, built into the hardware. And then the X bit was reserved by Intel. You guys can think whatever you want the X bit to do. We'll leave it at that. So, did they ever use it? Don't know that. Don't know that. I would be careful though in looking up X bit on a Google search, especially if you got a picture of some kind. I think that you might find yourself some area that could be more. Bottom line is, for those of you who caught that, apologies. For those of you who didn't catch it, don't play with it. All right. So, I can tell you more stories, but I'm already too deep into this to go any further. All right. So these are the other sets of bits, segment descriptors, the access rights sorts of things. Okay. So we talked about there's the brown stuff here. We're going to get into that more detail. The access rights. And then there's these fundamental bits, these segment descriptor bits, okay? And then label segment descriptor bits are these red ones here. That's on this slide. And then the additional access rights bits are down here, okay? When A is equal to 0, the segment is not accessed. Basically, it's a record whether the segment has been used or not. When you're talking about types, you've got 8 different possible types. You might want to declare a space read-only, or you can write to that space. You might have a stack that's read-only, or you can write to that stack. Again, code that's only going to be executed, or code that can be read, which means you can look at the base of the code itself as opposed to just running it. And then the code is execute only confirm that. I don't know exactly what's going on here, but I can add that up. All right. Again, if I want to ask questions on something like this, I'm going to ask you mostly to regurgitate what titles are, not so I understand all how they work. All right. So the S bit is system descriptor, okay? Or it's code data or stack. Okay, this is going to be kind of this is a particular address that's going to be tied only to the system. If it's a 0, if it's a 1, then you can use it for code data or stacks or normal kinds of accesses. See the description privilege level. I believe this is the point now where we're talking about those 4 different privilege levels. Remember, talked about way back in the beginning. You've got 0 is going to be the most privileged. 0 1 is going to be a little less. 0 1 0 is going to be even less. 1 1 is going to be normal type sorts of accesses. These sorts of things. I think DL is that selection there. And then the P bit is set for the descriptor being undefined. Or, in other words, we don't know where this descriptor is coming from, or this descriptor has been tracked down and has a valid access location. Okay? The access right byte controls access to protected mode segment and how the segment functions in the system. All right, so this is byte 5. Can back here. This is access rights. The 8 bits that sit here in byte number 5. Okay, and then byte number 6 contains the 4 new bits, completely unique, and then these additional L bits. Notice how the L bits 19 down to 16 tie in with the L bits 15 down to L0. That's probably your original 20-bit address field that you have had in the 8086, but now we're starting to push into the 286 and higher with this sort of protected mode stuff. Okay. All right. So the access bit, I'm going to set corrected on this. It's set automatically by the microprocessor. It's never cleared. Allows the OS code to track frequency of usage. So once something has been accessed in that particular field, it's going to set the access bit for that particular field. Present bit should be interpreted as being descriptor is valid. And that means what we're saying here is that you've got this massive amount of addressing space that in the wildest dreams of 286 we'll never be able to have access to. So the question is, you've got virtual memory taking place here. And that is the present bit means that particular segment or that particular chunk of code that you're looking for either exists in memory currently, or we're going to have to go out and get it and bring it back. P means it's present. If it's a 0, it's not present. The microprocessor will refuse an attempt to use it because it's not present in memory until your DMA, your direct mode addressing chip, goes out, pulls that segment out of memory and populates it in memory and sets this bit then to a 1. So meanwhile, the microprocessor is going to not access it. Although the AR must always be valid when P equals 0, the rest of the descriptor can be used in any way the OS likes. Okay, so if it's not present, then the OS can make some special uses out of this particular chunk of memory. The system bit indicates how the descriptor is to be interpreted. Okay. On that expect, I only see mention of it with respect to the 8086. Perhaps it's been removed. That's a real possibility, Matt. I wouldn't be too surprised if it's not around anymore. All right. S equals 1 indicates a code data or stack descriptor. So again, we talked about this. S0 is reserved for the system. Okay, the system only is going to be able to, we're talking about the most privileged level. If you have S equals 1, it means you have one of the 3 higher privilege levels to be working with there. Higher privilege, less protection. All right, in the non-system S equals 1 segment, type equals 0. The data segment is basically a ROM. Type equals 1. Both read and write operations are allowed. What he's trying to say here is that if the S equals 1 if S has been set to 1, then you're going to find type elsewhere. I was trying to figure out where the type part comes into play. I wasn't able to figure that out. So there may be some other function I'm not aware of. Bottom line is, if you have a system bit and type is equal to set to 0, you're not going to be able to write that memory. That's the whole goal in life, and that's protected in hardware more than likely. Type equals 1, now you can write to that memory. And then type equals 2 or 3, you're talking about a stack sort of function that's coming into play here. So stack segment ends 1 byte below the base address, expanding the segment, decreasing the limit. So bottom line, you're talking a stack function if you have type equals to 2 or 3. All right. So segment descriptors, if you're in protected mode, we talked about, remember, replacing the 1 with that we replace what to get the segment descriptor. We replace the selector. 13, yeah, okay. So we got the selector dynamic coming into play instead of the segment sort of thing. All right, sorry. Here we are. All right. So getting up here, segment descriptors in protected mode. There's a type 4, 5, 6, or 7. That looks an awful lot like 4-bit sorts of selection kind of thing there, or 3-bit selection sorts of things. Oh, are these the types? Ah, okay. Sorry, guys, back up. I'm going to stand corrected. All right. So type 0 is 3 zeros here, right? The data segment is basically a ROM. It says data read only. Everybody with me on that? I'm sorry, I was leading you guys I was getting confused myself. Everybody see that? Type equals 1 is 001. The data can be read or write. Okay, so you're going to protect the data that says that memory you can't write to it if you have a type equal to 0. And remember, these 3 bits now all fit into this type field here on the segment descriptor, okay, which is byte number 5 here in the new 64-bit segment descriptor protected mode addressing area. Okay, so back up one more time. So up here in byte 5, here's this type we're talking about, and now we're looking at the details of that type down here. So if type set to 0, he's just explaining all these things. Like, okay, now I get it. Apologies for not catching it right away. Data is read only if you have all zeros for that type field. If it's 001, means you can write to that RAM location, that memory location. If you have 2 or 3, you're talking a stack type function. And again, for 10, the stack is read only, kind of like the data only sort of thing. And it's typed, it says it's defined analogously to type 0 and 1, except now you're talking about the stack. Okay. So the stack, you can only read the value out of the stack, or you can write a value to the stack. And sometimes you want to do that to move the stack or locate it in a different location, or restore a stack would be some of the other functions you want to be doing, where you're going to be restoring a stack to where it was, where you're going to be writing the stack. But most times you're just going to be reading what's on the stack. You're not going to be changing directly how that stack is functioning. All right. So again, you can have the read only, where you can just read the information, or you can allow the user to be able to write that information as well. So now we get up to type 4. Okay. You're talking about a code segment. What determines this type? Is this set in the attempt to access, or can this data be queried for an address? So this type thing, this is where you're built into the address field itself. And you have this big gigantic address field now with the segment descriptor becomes more some of the address bits are sacrificed to keep this functionality. All right, so type 4, you're talking about a code segment with no read permission. Okay, that means you can't read it. How does the CPU determine, how does it does it in hardware? That's going to be the quick, short answer I'm going to give there, Matt. Good question, though. So we got type 4 is a code segment with no read permission. So what you're talking about here is you have the ability to execute the code. The code has been compiled. It's been created into a binary format like you guys have done with some of the earlier sorts of things in the class, right? Sometimes if the code isn't functioning and you guys were the ones who created it, what you want to do at that point is you want to say, well, why did the code go off the rails? You can reverse assemble. You can bring the code back out of the binary. There's other things you can do where you can kind of step through the code and these sorts of kinds of things. You guys have done that in the past. That you can do if you have a type 5 sort of thing where the code can be read back, where you can see what the code was. If you set the protection to 100 there, you're saying, nope, you can't even know what was going on in this code. All you can do is execute it. And frequently, that's all you really want to do anyway. I mean, how many of you guys want to ever go line by line through what the Excel code is that puts the spreadsheet on your screen? Almost never, right? So most times, a lot of the code is going to be execute only. Probably you're only going to be really too worried about this type 5 if you're a troubleshooter or you want to figure out what's going on. I always want to fox that poor Excel. Fix that poor Excel. Okay. Fox was a good answer. All right. Then we got type 6 and 7. Are these fixed modes? Again, I'm not sure how they're all selected and set up. I have to confess ignorance on this, but the idea is, and part of the reasons to go through this process is not necessarily to make you experts on protected mode, although you certainly are, we're opening a door here if you want to try and play with it a little bit further. What we are doing, though, is we're giving this kind of concept. And this is, again, remember, I've told you guys, I kind of want to get to a point where you guys get some of this idea of this mapping kind of sort of thing here, where you've got these different fields in an address range, and you pick out certain elements or certain bit ranges from these fields to understand what's going on. And the fact that in these ranges, in these fields, you start to get some specific bits that are doing unique things. That's the main goal. Not necessarily you're going to be experts in protected mode. And so if I do ask you any questions on this, it's going to be like, okay, what does bit P stand for? What function does bit P have? And then really, for the most part, all you have to do is regurgitate it. But the main goal is to get you guys to understand that in a bit field, there are, especially in the modern day, we got 64-bit fields running around everywhere, that these have different functions and different ideas and different things that are dedicated in a particular system for them. All right? All right. So, when your segment descriptor is when you're in the protected mode, and we're talking a segment descriptor now rather than a segment offset, these fields now become more unique. When we talked about the top 13 bits are the descriptor index. You're trying to choose whether you're going to use the global descriptor table, which is protected mode addressing, or if this is set to a 1, you're still going back to the original old-fashioned local descriptor table. I was right, LDT, local descriptor table. RPL, request privilege level. All right, so 00 is the highest. It's the most protected mode. It's that most privileged from the first slide, okay? 00 is back here. It's the red, okay? And if you work your way from red through to green, you guys were talking about your favorite colors. Work your way through from red to green, okay? You got red, you got orange, you got yellow, and then you got green, okay? So these are the protected levels. 00 is the central kernel part, and then you've got the next 2 device driver levels out here, and then when you get up to 1.1, you're talking about the application level then at that point, okay? So now let's see, descriptor table and table index. The 13-bit descriptor table selects one of up to 8K descriptors. Okay, let's talk about this for just a second. How much address spacing do I have with 13 bits, everybody? That's one of the reasons to dwell on this a little bit. 13 bits, how many addresses locations have? 2 to the 13th. Okay, that's cute. 8 KB. Okay. 8 KB, not 4 gig. Not 4 gibby. Come on, Matt, you're cute. All right. 10 is K. Oh, 13, not 32. Yes, 13, not 32. Okay. You stand corrected. So 13 bits is going to get you to 8K. And notice right here, magic, we got 8K descriptors in either the GDT and LDT as specified by the TI bit. So with these 13 bits, you're not looking into memory anymore. With these 13 bits, you're looking for an entry in this big, gigantic table. Okay, and you have up to 8K different entries in the table. That make a little bit of sense? Therefore, these 14 bits allow access to up to 16K 8-byte descriptors. Okay, so their point is that this is a 16-bit deep descriptor. The descriptor itself is 16 bits, and so if you're only working like in an old 8088, then at that point you would be talking about 16K 8-byte descriptors. Okay, RPL. This is the protection level. The desired privilege level of the program. Access is granted if the RPL value is lower, higher in privilege than the AR of the argument of the segment. Otherwise, a privilege violation is issued. So that what's happening is that the thing goes to try and get to a protected level it's not supposed to get to. Then the device you'll probably get a fault show up somewhere, and you probably won't get the memory or that location, what the data is at that location. Excuse me. All right, so here's the translation process. Okay, remember these are these different address fields. Does everybody recognize this? Okay, so here's the bottom 16 bits. Here's the next 20 bits. Okay, and then here's the access rights piece. I don't remember if that one was even labeled. Here's your let's go back up here. Hang on a second. Back here. All right, access rights. And then this one, so this one is the one that's the continuation of the limit, the lower part here. So let's go back down here. So this is the continuation of this lower down here to get you 20 bits. This is, remember, this is the one that's you're choosing what function you've got going. Those are those 4 unique bit things, right? The G, U, D, and X bit, the X bit that never got used, are sitting in this location here. And then the top then are the top 8 bits that go into place to create the base, and then you pick off these 2 pairs of bits to create the limit. All right, so instead of left shifting by 4 bits in real mode to form the segment address, we right shift by 3 bits and use the value as a table index. All right, so I'm not going to try and walk through this whole thing. All right, but the goal is that, again, we're going to use these address bit fields for unique applications, okay? And then that's going to help us to look up our segment in our index table, and then we're going to pull out our index table, and that's going to send us off into the particular memory we want to be working with. 3 different descriptor tables. Okay, now we're going to talk about GDT, which is the global descriptor table, LDT, which is the local descriptor table, and IDT, which has its own little unique area up here, the interrupt descriptor table. So exactly 1 GDT and 1 IDT must be predefined for protected mode operation. Remember, you don't have to be in protected mode operation. If you're in protected mode operation, you're going to be working off of the GDT and the IDT. If you're not in protected mode operation, you're going to be working out of the LDT, which is the more simple, less protected kind of sort of memory, and you're talking about some backward compatibility functions here. An LDT can optionally be defined on a per task basis, is used to expand the addressable range of the task, okay? And again, I'm thinking more when you're talking about an LDT, you're talking about also going back to some previous functionality there. All right, note that references to IDT are done through hardware interrupt mechanism and not from a program via a selector. Okay, so remember we talked about the interrupt table and so forth. You get an interrupt and you go to the memory, you find that particular interrupt level or where that particular interrupt bit is. It takes you into a unique point of the table. That table then gives you a memory location, you go to that memory location and execute the interrupt program that's found there. IDT is doing a similar thing at a little bit higher, more sophisticated level. There's more protection built around it. You may get an interrupt that can't be executed, or that's going to mess with the operating system, or not allowed to mess with the operating system, or an application or something else. Oftentimes, I would think that an IDT is going to be pretty low level. So that may be a whole new set of protections that are added there. All right, now we're getting even into nosebleed territory. But there is one thing to take away from this slide, okay? And that is this concept of an invisible register. There are registers that the programmer can see, and there are other registers that are buried in the hardware itself that the programmer can't get access to, can't mess with, or whatever kinds of things. And that was the main thing I want to take away from this slide, okay? The addresses of the GDT and IDT and their limits are loaded in special registers. Okay, these are again the invisible registers, the ones that the programmer can't see before switching to protected mode is possible. So what's going to happen is when you go into this protected mode, all right, as you go into that mode, the operating system itself is going to load some of this protected mode area up here with the values that it has based on the fact that you're either in protected mode, GDT and IDT. If you're in LDT, it's not going to mess with this stuff. It's going to be a very low basic kind of sort of thing. So programmable invisible registers. The other registers are enclosed by red dotted line are part of the descriptor cache. Cache is used to reduce the number of actual memory references needed to construct the physical address. Cache is what stores the information close by to the processor so that it can kind of get in and out of it quickly, and it keeps it local. There's one cache register for each of the 6 segment registers. Okay, I'll buy them on that. The base address, limit, and access rights to the descriptor are loaded from memory every time the corresponding selector changes. So when you go outside of an existing selector, you're going to go get a new chunk of memory, fill it in there, and you'll start operating out of that instead. Okay, we talked about the virtual memory. The LDTR and TR sectors refer to special system descriptors in the global descriptor table. So let's consider how the LDTs are used to expand the address space of the individual test. I'm going to probably shoot myself in the foot on this one, but anyway. All right. So I said, in my mind, local descriptor table, you were talking about stuff from the old memory, things. I may change my mind on that. Apologies for doing that midstream here. And again, I'm not looking, the main thing I was looking for here is just kind of the concept of invisible register, that it exists, not so much the details about applying any of this, all right? And I think we're getting to the top end here anyway. The local descriptor table selector indexes a GDT system descriptor describing the segment containing the LDT, while the cache stores the actual LDT descriptor, okay? And again, I'm not going to go into a lot of detail here. Bottom line is you've got several different levels of referencing that are taking place. I'm not going to put you guys through the details on this. I'm going to make myself a personal note not to quiz you on either of these 2 slides, so you guys don't get yourselves all discouraged and trying to figure it all out. This is, remember we were looking here then, bit 44, he's got highlighted in blue. Bits 40 to 43 are highlighted in red. Remember now that these are the bits that we were looking at a while back here, though. We're talking about these guys right here. All right, so he's actually got this color-coded now as he gets to the end, okay? And so here he's got them all set up as brown. But when we get up here to the end, we're one too many. When we're getting up here to the end, here brown is the first bit, and that's P, that's bit 47. That's the present bit. And I suspect if we go back here to this slide, I think we'll find P is the present bit. Yeah. Descriptor is undefined. Descriptor contains a valid base and limit. And then I think if we go up here, we'll find that 00, I probably just wasted space. Blue is the S flag. And I think if we go back up here now, I think we'll find that here is the S flag. Yep, blue is the S flag. This is okay, the 2 blacks are the privilege level. So I'm sorry, I'm going to stand corrected on that. And then he's once again giving an example. Whoop, sorry. Whoa, went too far. bring this guy back over here for now. Finish it up here. No, we won't. Give me one more second. Sorry, it popped out on me here. Give me a second. Oh, gee whiz. There we go. All right. Sorry about that. I went too far out. All right. That's got it back. Just to sit over here. Okay. So back to where we were. So the 3 bits 40 to 43 is the type field. I thought that would be 3 bits rather than 4. Nice Aladdin calendar. Thank you. That was back when our son, who's I think even a little older than you guys, was doing it back then. I can show you the world. Thank you, Colby. Anyway, I'm trying to think why he's got the 3 of them all red, or all 4 of them as red, when I think type and the segment can be accessed. Okay. So what's he doing with here? Bits, the type field is extended to 4 bits. Oh, there is no access bit. Okay, all right. So when you start getting into the LDT, the bits have a little bit different functionality, but it's pretty much the same. Let's go fly a kite up to the highest height. Mary Poppins, very good. All right, so I think that should be slide 16. Yeah, it is. All right. So 15 and 16, I will make a note. Class 19, slides 15 and 16 not to be on the final exam, which brings up a very good point here, and then I'll let you guys go way too early. I'm really cheating you of everything tonight, and I'm sure you guys feel completely cheated and unprivileged. We're into the last 2 bits. One out of the quiz 3 and midterm grades going in. Oh, I haven't put them up on Blackboard. Hopefully you guys know what your grades are for the quiz and the midterm, right? You already know what those are. I just haven't posted them. I'll make that note, though. Post grades. I'll do that. Colby, I think you should. Oh, is there somebody that I haven't talked to about their midterm, by the way? Somebody did send me a text. Send me a text one more time. If you don't know what your midterm grade is, send me a text and I'll try and look at that. Not guaranteed to be the next 24 hours, but if it drags into Saturday, I'll get you the response. I got to grade the quizzes anyway. All right, so back to where we're at here, and this mouse wants to be here. So everybody knows a couple things real quick then about announcements, and then I'll let you go. We did talk about the early final as people were coming in. The way the early final is going to work is we will still have it, but it will be a little bit different type parameters. I will put the early final up for those who want to take the early final. I will put it up at the beginning of the normal class period on Monday, the 11th of May. That would be at 5:30. The final exam, the early final exam, will go up at that time. Okay, it will only be up for that period. So if you want to take the early final exam, you will need your proctor to be available for you to help you take that. I'm not going to be able to get around that, I'm afraid. If you can't have the proctor available, then you'll have to take the final at the normal time slot, which would be Monday, May the 18th. I will be there on the 11th of May. I will keep the final up for at that point. There's no reason not to give you the full 2 hours. We'll give you the full 2 hours for the early final exam. If some of you come in and everybody gets all done early, then we'll shut it down a little early, but I'll give you up to 2 hours for that. And then the regular final will take place on May the 18th. We will do the same thing there that we have done for the midterm and the other quizzes, and that is I will put the final exam up on the 18th at 5:30. Is the early final time on the calendar. It would be the normal class time, Andrew. So I will give you a full 2 hours, but it will start at 5:30 like a normal class would. Same thing on the final exam as well. It'll start at 5:30, and I'll be there from 5:30 to 7:30 on both dates. Okay, and then I can answer any questions. If you can't get a proctor to be with you on May the 18th, Monday, May the 18th, then what we'll do is you'll have 48 hours to do it like we have, but you won't have me there then to talk to you about it. I do hope we're back to regular restaurant stuff by then. All that's kind of being very hopeful. That will be my 35th wedding anniversary, for those of you who are wondering. And I married my wife when she was 5. Thank you, Colby. She looks like I married her when she was 5. Anyway, I look like I got married when I was 40, but anyway. All right. So that's the information about the final. I will, on the next slide on Monday, May the 4th, make a note on this too. Slide set 20 will have a review set, a review table like I've had at the other ones, you know, the slides to pay attention to. We should probably have enough time to get into it. I'm not going to spend a lot of time on paging segmentation. We'll see where we're at, whether we even need to have the class on May the 6th or not. Hopefully I can get the final reviewed on the on May the 4th, and we can maybe even just take a night off then on May the 6th. Any other questions on all of this? I better know that May the 18th is my anniversary, that's for sure. Okay. Well, seeing no further questions, I think we're about done here. I'll stick around for another 5 minutes or so, 5 or 10 minutes. If anybody wants to ask me a question, you know, a little bit more. But if I see most of you guys gone in 10 minutes, I'll shut the service down tonight. Thank you, everybody else, for coming. Thank your proctors again for me. I can't say that enough. And we'll see you all, guys, on Monday, May the 4th. I will get the quizzes graded this weekend, is the plan.